Hello, George Romanic here. Welcome to Fundamentals of Weather and Climate playlist. In today's video we are going to discuss nighttime evolution of the temperature and how that leads to something that we call temperature inversion. What is temperature inversion? It's a situation when temperature is not doing what it is supposed to do, and it is supposed to decrease with the height. But in certain conditions temperature can increase with the height, and we call that temperature inversion. Let's see how that can happen during night times. We will start by once again examining 24-hour evolution of the temperature. So if the y-axis is temperature and we start with midnight 00, and then here we have sunset at 6 a.m. and then we have local noon 1800, and finally here we have midnight of the next day. And we said temperature typically evolves that if we start with certain value of temperature at midnight, it is decreasing until sunrise, and then it starts increasing until approximately 4 p.m. local time, and then temperature continues decreasing, perhaps matching the value from the previous day at midnight. Now, in my previous video, we study daytime conditions. So if you are interested to understand this part of the curve, check my previous video. Today, we study nighttime. And the same applies for this part of the night. Well, to study this, we will consider energy balance at the Earth's surface. So the x-axis will be the same time axis, starting from midnight, and then here we have sunrise at 6, we have local noon, and we have sunset at 1800, and then we have 2400 hours. But the y-axis here is the rate at which energy is either being absorbed by the surface or being emitted by the surface. And please study my videos on the energy budget and radiation to understand everything that I will plot here. I discuss that in really great details in those videos. In principle, we have two energy fluxes associated with radiation. One is shortwave radiation that we receive from the sun, and another one is long-wave radiation that the Earth radiates back into the space. Now, if we consider these two fluxes, then it is clear that shortwave flux associated with sun's radiation does not exist during night because there is no sun during night. So the red curve associated with solar radiation exists only during the day, and the peak is at local noon. But we also have long-wave radiation that the Earth radiates back into the space, and that flux might look something like this. If we start with some value at midnight, then the long-wave radiation flux will decrease with time until sunrise, and then it will increase until sunset, and then it will continue decreasing, perhaps matching the value from the previous day. And just to refresh your memory, the red curve we called it K star, and the blue curve we called it L star. Net shortwave radiation and net long-wave radiation respectively. Now we also said when the blue curve is above red curve, the surface is losing energy through long-wave radiative flux. In other words, you can visualize that the surface is radiating energy like so. And the same is happening here. Whereas when the red curve is above blue curve, we have sufficit of energy at the surface, and the surface has net gain of energy through absorbing shortwave solar radiation. Now, it is very clear, therefore, that K star solar radiation is 0 during night. So during the nighttime period, the surface is losing energy. Because surface is losing energy through long wave radiation, the surface is cooling. And because it is cooling, the air supplies its heat, its energy to the surface. And therefore, temperature of the air is decreasing because air gives its own heat to the surface, which in turn is losing energy through this long wave radiation. I want to schematize that here, say like this. If this is the surface, and that surface is losing energy through these long wave radiation fluxes, then air, I will represent air with these dots like molecules of air, then the air is giving heat to the surface because it's warmer than the surface through the flux of sensible heat, which we called QH in previous videos. Please check that video. Now you might say, but wait a minute, the air is also radiating energy in the form of this long wave radiation. You are right. The air is also radiating energy, but the air is much poorer radiator of energy than the surface. In other words, in a given unit of time, over 1 hour, let's say, surface will radiate much more energy than the air. And therefore, surface becomes colder than the adjacent air, and therefore air, being a warmer body, heats the surface and consequently loses its own temperature as schematized over here. And that is why minimum temperature is observed at the time of sunset, because the surface was continuously cooling, emitting long wave radiation, and the air, poor air, was continuously warming the surface. So if we look at this concept, it is not that difficult to understand, I believe, the concept of temperature inversion. To study temperature inversion, let us plot the profile of temperature, which is on the x-axis, against height, z, which is on the y-axis. And we will focus only on the first several meters, let's say first 3 meters above the surface. You see, temperature at the surface is low because surface is radiating energy, and the air is heating the surface through sensitive heat flux. Which air is going to heat the surface most? Answer: the air that is closest to the surface, which means that air will be colder than the air further away from the surface, which means temperature tends to increase with the height in these first few several meters. And this is not, as I discussed at the beginning, what temperature is supposed to do in the troposphere, and this is why we call that inversion. That sometimes means if you are, let's say, 180, your height is 1.8 meters. In very cold night conditions, temperature at your feet can be freezing, but temperature at the level of your head can be above freezing. So your feet might be exposed to much lower temperature than your nose and your head. Now we should also introduce the concept of wind here, because you remember when we studied daytime evolution of temperature, we saw that wind can have profound influence on how heat is distributed in vertical direction. And it turns out that that is also the case during night. The coldest nights are when we have no wind, when we have calm conditions. And the temperature profile might be like so. When we have windy conditions, the temperature profile might look something like this. Perhaps we also have inversion, but the inversion is not as pronounced as when we have calm nights. So this is windy, this is calm. The question, of course, that some of you might ask, why the difference? The difference is when we have windy conditions, as I discussed in previous video, we have extremely good mixing between different levels in the atmosphere, which means this warm air is brought down, this cold air is brought up, and everything is mixed so that you get more or less uniform distribution of temperature. Not quite uniform, temperature is still decreasing with height, but not at the rate in calm conditions. Lastly, how clouds affect this nighttime cooling? Well, we saw in the previous video that when we have daytime conditions, clouds are very good at reflecting incoming solar radiation and thereby reducing temperature at the surface. But during the night, they actually warm the surface. That is because clouds, while reflecting solar radiation, are extremely good at absorbing long-wave radiation that the Earth radiates. And then they are also good emitters of that radiation, and they send it back to the surface, thereby warming the surface. Namely, if this is the surface of the Earth, and the Earth is losing energy through long-wave radiation, in the absence of clouds, that radiation might go into the outer space and never come back. But if we have a cloud, then these clouds are extremely good at absorbing this radiation. And then what do they do with it? Well, what they do with it is they send it back to the surface. I put it as a red because that means they are warming now the surface. And the temperature of the surface is therefore higher than what it would be if there was no cloud. So please, when you know this, a little bit pay attention, and you will see that cloudy nights are always warmer, everything else being equal, than the clear nights. And the reason is what I just discussed here. Previous video discussed daytime temperature evolution. This video discussed nighttime temperature evolution. You know so much now. You can walk down the street, whether it is day, whether it is night, doesn't matter, and you understand how temperature is changing. Until next video, goodbye.